In this module, we will cover life cycle assessments for asphalt paving projects in Washington State. In 2022, the Federal Highway Administration began their Climate Challenge, an initiative that seeks to lower emissions in the transportation sector through changes in material selection and design. After WSDOT applied for and received funding for this project, a study was undertaken through the University of Washington and the Carbon Leadership Forum, in which life cycle assessments were performed on 4 different asphalt paving projects across Washington State, focusing specifically on LCA modules A1 through A5. These projects were tracked over the course of the 2023 paving season and relied on the following information from owners and contractors. For the material production phase, or modules A1 to A3, EPDs were collected along with material types and quantities, such as emulsified asphalt or joint adhesives. In A4, trucking hours were considered for material transportation, while in A5, construction equipment types and hours operated were factored in. After visiting each project site and collecting data from contractors, the research team compiled and analyzed this information in the Open LCA software. This program uses project-level information, such as material quantities and life cycle inventory data, to perform life cycle assessment, visualize processes, and report environmental impact results. Results from this analysis can be studied in several ways. The following charts are from University of Washington master's student Aaron Lum's thesis presentation, representing the embodied carbon emissions for these 4 paving projects. This first figure shows the total global warming potentials for each job site, as well as their average. Each bar is broken down by life cycle stage and follows the same ordering as the key on the right. For example, emissions from trucking the hot mix asphalt from the production plant to the job site is represented by the blue bars highlighted here. Take a look at the text near the bottom of each bar. While all 3 jobs involve similar hot mix asphalt paving work, they differ from one another in material quantities, constituent materials, and even some construction processes. Since the material quantities are different for all 4 jobs, it is difficult to directly compare these jobs. This next chart allows for better comparison by normalizing this data on a per short ton of hot mix asphalt basis. This graph shows the amount of emissions per ton of hot mix asphalt placed. As you can see, job 9914 was the largest emitter per ton of asphalt placed, while job 9954 was the smallest emitter per ton of asphalt. On average, these projects emitted about 75 kilograms of CO2 equivalent per ton of asphalt placed. This figure breaks down emissions by life cycle stage as percentages of each job's total global warming potential. We can further simplify this graph by grouping emissions into 3 basic categories: material production, A1 through A3, mixed transportation from the plant to the construction site, A4, and on-site construction, A5. There are a few things to notice in this new, simplified graph. First, materials production is the source for a majority of carbon emissions associated with these paving projects, ranging from 65 to 81% of the total, with an average of 72%. Second, as you might expect, mixed transport carbon emissions vary with transport distance. Longer transport distances result in higher carbon emissions. Transport distances from 35 to 45 miles contributed carbon emissions fractions from 16 to 21%, while the job with a mixed transport of only 18 miles contributed just 10% to its emissions total. Therefore, less transport distance will result in less emissions. Finally, construction activities on site account for a relatively small fraction of project carbon emissions. A few other observations from this study follow. Asphalt binder material production was the largest contributor within materials production. So, any activity or decision that lowered the amount of virgin asphalt binder in a mixture contributed to a reduction in overall project carbon emissions. Therefore, using more reclaimed asphalt, or RAP, is associated with lower carbon emissions because the asphalt binder in the RAP reduces the amount of virgin asphalt binder required and its associated emissions. Mixtures using modified binder had higher carbon emissions due to the carbon emissions from the modifiers. However, modifiers often make for more durable asphalt binder and longer lasting pavements. So, as with all observations here, we must carefully interpret lower emissions in the materials production through construction stages, A1 through A5. It may be true that a modifier increases a mixture's A1 through A3 emissions, but if the pavement lasts longer because of it, the overall lifetime carbon emissions from the pavement may be significantly less. This brings up two important points. First, EPDs that only account for life cycle stages A1 through A3, or even this study that accounts for life cycle stages A1 through A5, do not account for a roadway's operations, use, maintenance, rehabilitation, or end-of-life actions. So, decisions on pavements or materials should not be made based on initial materials production and construction LCA data alone. They do not tell the whole story. Second, LCA data only account for a limited set of environmental impacts and therefore should not be used by itself to assess pavements and roadways. Rather, LCA and associated EPDs should be used as one evaluation method out of many in selecting, designing, and constructing roadway projects. When focusing on transportation, researchers found that Module A4 contributed about half of the emissions that A1 did, 17% on average. Standardizing this based on each project's travel distance, the data showed that each mile trucked contributed nearly half a kilogram of CO2 equivalent per short ton of asphalt. Out of all the construction activities, which accounted for 11% of emissions on average, the milling machine, roller, paver, and material transfer vehicle were found to be the largest contributors. While these trends were observed under the 4 projects in question, several limitations must be emphasized. This was a limited study with only 4 jobs analyzed across the state. Fuel consumption data for trucking and construction equipment was not as specific as it could have been. Double cycling and backhauling, 2 trucking processes that occur often to save money, also can reduce emissions by reducing total trips. This, however, was not considered under the scope of this study. This research project found valuable information on emissions resulting from the pavement projects used, but broad generalizations about the industry should be avoided. However, EPDs are clearly a successful avenue for carbon reduction efforts, as the materials being used in pavement, particularly the asphalt itself, contribute a significant deal to a project's total emissions. Future studies should aim to collect mix EPDs, transport distances, construction fuel consumption, and tack coat usage.